Hello, calculus students. Okay, so what we're going to do now is do a Taylor polynomial, but we're going to have the Taylor polynomial never stop. We're going to use this formula for Taylor polynomials. The only difference is I'm going to change this to an infinity and just turn it into a series. In this case, it's going to be called a Taylor series. So Taylor series centered at x equals a. The formula for it is given here. The first term is just f of a by itself, but you could imagine there being an x minus a to the 0 and divided by a 0 factorial, but these two things are 1, so we don't write them. The next term is a first derivative evaluated at a, but then there's an x minus a to the 1, and then you could put this over a 1 factorial if you like. The next term is second derivative over 2 factorial, and x minus a is being squared. The derivative, the factorial, and the power are always the same number. So a third derivative, a 3 factorial, and a power 3. And just do this forever. So the general form is the kth derivative, k factorial, k power, and k starts at 0 up to infinity. The Maclaurin series. This Maclaurin series is really just a Taylor series, but specifically one that's centered at 0. So if I were to take the formula up here and change all the a's to zeros, it would turn into this formula. Okay, our first example, we're going to make a little table. K is going to keep track of which derivative we're on, and then we're going to figure out what the kth derivative of the function is. And then specifically, we're going to figure out what the kth derivative of the function is evaluated at where we're centering this. So in this case, at 2. So when k is 0, that just means you're not doing any derivatives. You're doing the 0th derivative. That would just be the original function, which I'm going to write this way. When k is 1, it just means do the first derivative. Second derivative, do another derivative. Third derivative. Let's just do one more. Now you want to plug 2 into all of these derivatives. 4 times 2 to the minus 1, that's going to just give us a 2. Minus 1 here, a positive 1 here, negative 3 halves. We have 96 over a 2 to the 5th, that's over a 32. We just get a 3 out of it. Then we start constructing the Taylor series. Let's say t sub infinity for our Taylor series. We do f evaluated at a, in this case a is 2, plus f prime evaluated at a times x minus 2, plus a second derivative evaluated at 2 over a 2 factorial, which is just 2, times x minus 2 squared, plus the next one will be the third derivative evaluated at 2 over a 3 factorial, which is 6, times an x minus 2 cubed, and then we have room for our last one. A fourth derivative, so we'll put a 4 in parentheses there, evaluated at 2 over a 4 factorial, which is 24, times an x minus 2 to the 4th, plus dot, dot, dot. Okay, now what we're going to do is replace all the derivatives evaluated at 2 with these numbers we have here. So we're going to change f of 2 to 2. Then we're going to change f prime of 2 to negative 1, etc. And at this point, let's go ahead and recopy this line here, but let's simplify some of these coefficients. So we have negative 3 halves divided by 6 is going to wind up being 3 halves times 1/6, 3/12, so it's going to give us a 1/4. And this coefficient is 1/8. Here's the makings of our Taylor series. And one challenge is going to be how to express this using summation notation. Let's start at k equals 0 and go up to infinity. Now the first obvious thing to me is that there's involved an x minus 2 to the k, because when you plug in k equals 0, you don't have an x minus 2. When you plug in 1, you get this term, right? When you plug in 2, you get that term. When you plug in 3, you get that expression, etc. Sometimes it's helpful here to put a little reminder of what the k's are in each step. The next thing that's obvious to me is that we have an alternating series. The signs are in fact changing and they start positive. We're going to need an alternating component, so a negative 1 raised to the k or raised to the k plus 1. You have to pick between those two so that the alternating signs are correct. Let's just try k and just test it. When k is 0, this will be positive. So the first term should be positive, and it is. When k is 1, this will be negative. So when k is 1, we get a negative term. When k is 2, we get a positive. When k is 3, we get a negative, etc. Now the next trick is, how do we generate this 2, then there's a 1 there, then a half, then a quarter, then a 1/8. You start to pick up on a pattern pretty well that to go from 2 to 1, you cut in half. To go from 1 to a half, you cut in half. To go from 1/2 to 1/4, you cut in half. And you keep cutting in half. It appears that the coefficients are following a geometric pattern. So we need to come up with a geometric pattern, something that starts at 2 times. We need things to be cutting in half, so we need a 1/2 to the k. And let's just test this and see if it works out. When you plug in k equals 0, this will become 1, and 1 times 2 is 2. So it does give me that first coefficient. When k is 1, we get 1/2 to the 1 is a half, times 2 we get 1. So we get the 1 that's in front of this term there. This appears to be working. Let's see if this term here gets produced when k is 4. And we're going to verify all of this. So plug in a 4 for here, here, and here, all the k's. And plugging in here gives us a positive, so check. Plugging it in here gives us x minus 2 to the 4th, check. And plugging in 4 here, we get 1/2 to the 4th, that's 1/16, times 2 is 1/8, so we get the correct coefficient here as well. All right, so here's our Taylor series, and we've expressed it in summation notation. See, let's make sure we followed all these instructions here. We expressed it using summation notation. We did that. Write down the first 4 non-zero terms. That's done. There's the first, the second, the third, and the fourth. We actually did 5. The last step, give the interval of convergence. So if you recall, we're going to use the ratio test on this. So that means we start with some absolute values. We rewrite that expression, but put k plus 1s everywhere instead of just k's. And we're going to divide this by the same thing, but just k's. And then we do as much simplifying as we can. Let's see, all the negatives are going to cancel because of the absolute values. Simplifying this over this, we just get 1 copy of x minus 2 up top. These 2's here cancel, and then this will cancel with the k plus and leaving just 1 copy of 1/2 up there. And this you can say is 1/2 absolute value of x minus 2. Notice that there are no more k's left in this case. So if you do a limit as k goes to infinity, this just approaches itself as k goes to infinity. This is the capital K we get from the ratio test. And in order for this series to be convergent, we want that capital K to be less than 1. And then we solve this inequality. So I'm going to double both sides, create a double inequality out of this to get rid of those absolute values, and then add 2 to all sides. So x itself has to be somewhere between 0 and 4 for this series to be convergent. The next idea is to test the endpoints. So let's test x equals 0 and rewrite the series. Change the x to a 0. This is going to do a whole lot of simplifying. Since there's 3 things being raised to the k, just multiply all the bases together. We have -1 times -2 times 1/2 is 1. This just turns into a series of 2, which really means that it's just adding 2 forever. So it's clearly divergent by the divergence test. Okay, now we're going to test the other endpoint. We're testing x equals 4 next. Go back up to here and plug in a 4 for that x right there. And you're going to get 4 minus 2. You're going to get a positive 2 this time inside those parentheses instead of a -2. Okay, the same idea. Multiply all of the insides of those parentheses. So multiply -1 times 2 is -2 times 1/2 is -1, and that's still being raised to the k. So there's -1 to the k still present here. The last time there was just a 1 to the k, which is just 1. But this turns into a series that's just 2 minus 2 plus 2 minus 2 plus 2 minus 2 plus 2 minus 2 forever. The sequence itself is divergent, so the series is divergent by the divergence test. So our interval of convergence for this problem is just 0 to 4. And there's our interval of convergence, and here is our other 2 answers here. What this is suggesting is that as you do higher and higher degrees, we see that the polynomials are getting closer and closer to matching the graph, and they're doing so within the interval from 0 to 4. But if you go outside that interval, you can see that we have the blue quickly diverging away from the red. So the mimicry, if you will, is only happening between 0 and 4. Over here, we do not have the blue and red matching at all if you go left of 0. Okay, now there's going to be several more examples. I'm going to do some of the skipping of the determining what the interval of convergence is because we've already have lectures on how to do that. I'm going to show you how to create the Taylor series, this part right here, and then I'm going to just give you what the interval of convergence is, and I'm going to leave it to you to verify on your own. All right, let's do our next example. Notice this one is asking for Maclaurin series. Well, this is just a Taylor series when a is 0. So I still want to start this by doing a table. Well, the 0th derivative of this function just means the function itself. So I'm just going to rewrite the function, but I'm going to write it with a -1 power just to prep myself for the derivatives that are about to follow. K is 1 means do the first derivative. So the negative drops down. We get 1 minus x. The new power is -2. But don't forget the chain rule. This is going to output another -1 because the derivative of the inside is -1. Well, this -1 and that negative are going to combine and become a positive in the front. Second derivative, right? The -2 drops down. We get this 1 minus x. The new power is -3, and the chain rule happens again. Another -1 pops out. Well, this negative and that negative will cancel, making positive. Now, this pattern is going to keep happening. We're going to do -3 times -2, get -6, but that -6 will go back to +6 after the chain rule happens. Let's just do one more. Also notice that in the front, we have factorials happening, right? This coefficient's 4 factorial, that one's 3 factorial, 2 factorial, there's a 1 factorial, and a 0 factorial. Now we want to do the kth derivative evaluated specifically at a, and because this is a Maclaurin series, we're going to use 0 here. So just plug 0 into all of these functions and see what you get in each case. If this is a 0, that just goes away, so we have 1 in the parentheses, and 1 to the -1 just means 1 over 1 to the 1, which is just 1. The next one, plug in 0. We get 1 to the -2. That's 1 over 1 squared. That's also just 1. In fact, all of these parts are just going to become 1. So we're really just going to get the coefficients. So here's our table. If you were to say, hey, what's the 5th row is probably going to be a 5 factorial here. 5 factorial is 120. The 6th one will be a 6 factorial, which is 720, etc. All right, now we're going to construct the Maclaurin series. If you want to remind ourselves this is actually Maclaurin, you can use an M. Okay, the first term of the Maclaurin series, f of 0. The next term will be f prime of 0 times x. Third term will be the second derivative, evaluated at 0 times x squared, and then over a 2 factorial. The next one's going to be a third derivative, evaluated at 0 times x cubed over 3 factorial. And then we did one more, so let's do a fourth derivative, evaluated at 0 times x to the fourth over a 4 factorial. And then don't forget the dot, dot, dot. This goes forever. F of 0 is right here, it's 1. F prime of 0 is right there, it's also 1, so we just get x. F double prime of 0 is 2, right, so that goes in 2, but you divide that by 2 factorial. 2 over 2 is just 1. Now we're looking at the third derivative, which is 6, that goes in right there, but that's over a 3 factorial. They're going to cancel, leave a 1. All of the coefficients are going to be 1s. Now to write this in series notation, we just have powers of x. This starts at k equals 0 and goes to infinity. Now the interval of convergence, I'll leave it to you to verify, but it's going to be from -1 to 1. I don't know if you noticed this, but this series is also just a purely geometric series. To go from term to term, all we do is multiply by x. And the ratio is x here. And we already know geometric series converge when x is between -1 and 1, confirming our interval of convergence. And we know that it converges to the first term, which in this case is 1, divided by 1 minus the ratio, and the ratio is x. So notice what we just accomplished here. In trying to get more and more derivatives of a polynomial to match the derivatives of this non-polynomial, we wound up recreating the geometric series. Effectively, it boils down to if you can create a Maclaurin or a Taylor series from a function, and you find that that series converges for a certain interval of x coordinates, then it's true that the function and the series are equal to each other on that interval. So the conclusion here is that the function we started with is equal to the series that we just created from it, which is equal to 1 plus x squared plus x cubed, etc. But this equality right here is only true if x is an element of the interval of convergence. Now let's go to Desmos, and I want to show you visually what's happening. Let's change that function to 1 over 1 minus x. And I'm just going to slowly start typing out this. I'm just going to keep adding more and more terms to it. Let's add to that x. There's the first degree polynomial. Let's add to this x squared. There's the second degree polynomial, x cubed. Now we could also type in the series notation. Start at k equals 0, and let's end on capital N. Now capital N already has a slider for it, so I can use this slider to control where it ends. Now as I change this n, we are getting higher degree polynomials. But notice that the blue graph and the red graph are only becoming similar to each other for certain choices of x. Right? It seems like the blue graph and red graph will never match each other left of x equals -1 or right of x equals 1. In fact, it's only between x equals -1 and 1 that we're seeing the blue graph get closer and closer and closer to the red graph. And in theory, as we go forever, if we do a Taylor series, the series will be equal to the function. The blue graph and red graph will become the same thing, but only between x equals -1 and 1. Okay, let's do the next Maclaurin series. Okay, so here's the 0th degree, the original function. First derivative is the same. In fact, all of these are going to be the same, right? This is a nice, easy one. Since this says Maclaurin, we're going to plug 0 into these. So plug 0 into all these derivatives, you just get 1 back for all of them. Okay, so here's our setup for doing any Maclaurin series. So in this case, f of 0 is just 1, f prime of 0 is also 1, f double prime of 0 is also 1, so there's going to be a 1/2 present there. F triple prime of 0 is also 1, so it's going to be a 1 over 3 factorial, which is a 1/6. The fourth derivative evaluated at 0 is also 1, but over a 4 factorial, so that's a 24, etc. In summation notation, this is simply powers of x divided by those factorials. We've already shown that this interval of convergence is all choices of x. This factorial dominates this exponential. Denomination happens in such a way that the series will always be convergent no matter what x is. That means that the function I started with, e to the x, is actually equal to this series, and this statement here is true for all x. All right, and the series looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. This is another easy one that we can just program into our Desmos and just see what's happening. We're creating higher and higher degree Taylor polynomials centered at 0. As the series includes more and more and more terms, notice that the polynomials are matching the exponential curve, not only in the immediate area near where it's centered, which is at 0, but the blue curve and the red curve are becoming the same thing further and further and further away from where it's centered. This is an indication that we have a very wide interval of convergence. And in this case, we know that that interval is -infinity to infinity. Okay, now the next one, a natural log graph. So the 0th derivative of this function is just the original. The first derivative, the derivative of log of a function is function prime over function. Well, the derivative of the inside is 1, so that goes up top, and the bottom is just what that argument is. So it's 1 over 1 plus x, which I'm going to rewrite as 1 plus x to the minus 1. Okay, the negative 1 will drop, the 1 plus x will be rewritten, the new power will be minus 2, and the chain rule outputs 1. So the sign here in the front is going to stay. Positive 2 times 1 plus x to the minus 3. Fourth derivative, negative 6 times 1 plus x to the minus 4. Let's stop there. Now we're going to plug 0 into all of these. Plug in 0 for x here, we get natural log of 1, and natural log of 1 is also 0. Plug in 0 now for this x, and we get 1 to the minus 1. We get just 1. Next time we're going to get a minus 1 and then a 2. We're just going to get the coefficients, but the coefficients will be changing sign. Also notice that the coefficients appear to be one number less in factorial. In other words, when I'm doing the fourth derivative, I see a 3 factorial here. Let's just test that. If I do a fifth derivative, 24 times 1 plus x to the minus 5, plug 0 into that, we just get 24. And sure enough, when I do the fifth derivative, I see a 4 factorial. Fourth derivative, 3 factorial. Third derivative, 2 factorial. Coming back up to here, first term is just 0. Next one is positive 1 times x. Then we have a minus 1 times x squared over 2. Then we have a third derivative was 2. That'll be over a 3 factorial, which is going to be 6 times x cubed. The fourth derivative evaluated at 0 was minus 6. So we're going to have a negative term here, a 6 up top, and a 4 factorial, which is a 24 down below. Let's see if we can pick up on the pattern here. We start with x this time. We have minus x squared over 2, plus x cubed over 3, minus x to the 4th over 4. Do you see a pattern here? You can guess what the next one is. Plus x to the 5th over 5, minus x to the 6th over 6, etc. That's because, as we notice, this offset factorials over here. When k was 5, the numerator has a 4 factorial. This top right here is a 3 factorial, and that's sitting over a 4 factorial. That's just going to leave a 4 down in the denominator. And this offset factorials for every term is just going to leave simple numbers in your denominators. All right, so in series form, this looks like... Now, to be consistent, let's go ahead and insist that we start our series at k equals 0 like always. Let's see if we can figure this out. We definitely have powers of x, so I'm going to put an x to the k going on here. But I want it so that this produces this one here. I want the k equals 0 term to produce this x to the 1. So the way this is currently written down here isn't working. We want the power to be 1 more than what k is at every step along the way. So I'm just going to put a k plus 1 on this x. And that should solve that problem. And we have a denominator that's also always going to be 1 more than what k is. Now we've got to get the alternating sign in place. Let's just assume that this is correct to start with, and let's just double check it. Plug in 0 for k, this becomes positive 1 in here, check, it works. When you put a 1 in for that k, you're going to get a negative. All right, so there's our series starting at k equals 0. Now the interval of convergence for this one, I'm going to leave this to you to calculate on your own. It's going to be a radius of 1, but you're allowed to include the right endpoint, but not include the left endpoint. So what this is suggesting is that the original function I started with is equal to this series. And that series, if you wanted to, write out some of the terms. But this equal sign right here is only true if we pick x coordinates that are somewhere more than -1, but less than or equal to +1. All right, let's explore this one with Desmos as well. So between these two vertical lines, the blue graph will get closer and closer to the red graph as we do higher and higher powers. But we only get convergence of the series to the function if we stay within -1 and 1. Sine of x, we're going to see something interesting happen. When k is 0, the 0th derivative just means the original. So we have just sine of x. We have cosine of x next. Second derivative goes to negative sine of x. Third derivative goes to negative cosine of x. Fourth derivative goes back to sine of x, and then we repeat the cycle. Now let's plug 0 into all of these, because we are doing yet again a Maclaurin series. Sine of 0 is 0, cosine of 0 is 1, and back to 0, then to -1, then to 0. This is just going to keep repeating. The first term is just 0. Next term is 1x. Then we get a 0 term again. Then we're going to have a negative term. It's going to be an x cubed over a 3 factorial. Then the fourth one will be 0. There's going to be a fifth one, and it's going to go back to positive. It's going to be x to the 5 over 5 factorial. The sixth one will be 0 again, then back to -1 this time, so it's going to be minus x to the 7 over 7 factorial. Keep the pattern, this is what will keep happening. Rewrite this and get rid of all these zeros. Okay, our challenge is to write this in summation notation. We definitely see some powers of x happening, but let's see what happens if I just leave it like this. Plug in 0 first, we get x to the 0 is 1, so we do not get this. So I think, okay, we need to offset by 1 again. Now keep in mind that I want, this is the when k equals 0, this is what we get when k is 1. You can't skip k's when you're doing a summation notation, so it has to go through all the k's. So we're going to have to be clever about how to get the terms we want, even though the k's can't skip anything. Currently, this k plus 1 is not doing it for me then, because when you plug in 1 into k plus 1, you get 2 as the power. We want to get 3, right? In fact, if you just look at the powers, you want them to be the odds. to create a generic odd number is to double a number and then add 1 or subtract 1 to it. Let's test this out. Plug in 0 for k. We get a 1 in that exponent. Check. Plug in k equals 1. We get this 3 exponent. Check. Plug in k equals 2. We get this 5 exponent. Check, etc. All right, so we found a way that even though the k's can't skip numbers, we're only producing odd powers on x. Next, I see an alternating sign again, a -1. Let's just put a k and see if it works. When k is 0, we get a positive. Check. When k is 1, it will be negative. Check. When k is 2, it will be positive, etc. So this works. The other is that we have a denominator that's a factorial. Right, so this factorial, the 3, matches that 3. And that's true for all terms. They all match. So whatever this exponent is, just use that same formula and put a factorial on that. All right, plug in k equals 0. 2 times 0 plus 1 is 1. 1 factorial is 1. And dividing by 1 is 1. So right, there's a 1 here. We just don't need to write it. Plug in k equals 1. We'll get a 3 factorial down there. Plug in k equals 2. We'll get a 5 factorial down there, etc. All right, so here's our series that produces all these terms that have only the odd powers. And it can be shown that the interval of convergence is, in this case, also negative infinity to infinity. Again, this factorial will dominate this exponential in such a way that this fraction shrinks to 0 quickly enough so that this sum is convergent. I leave it to you to use the ratio test to confirm that. Interval of convergence is negative infinity to infinity, suggesting that the function I started with, which is sine of x, is equal to this series, which is equal to these terms. So this entire statement is true for all x. All right, let's watch this one happen. And when we do our series, here's a first degree. Now here's the third degree. When n is 2, we'll have a fifth degree. Now I'm just going to play n and watch what happens. The polynomials, which are blue, are going to get more and more like the sine wave, and it's going to happen further and further away from where this was centered, which is at 0. All right, so this is suggesting that the series and the sine wave are the same, and you can pick any value of x. All right, this next one is x plus 1 to the 1/2. Instead of putting a square root, I'm going to use a power. First derivative, 1/2 drops down, x plus 1 gets repeated, new power is -1/2, and chain rule outputs a 1. So the chain rule is not going to have any effect in this case again. Second derivative. In this case, it can be extremely helpful to not multiply the fractions together. Let me show you why. The next term is going to be 1/2 times -1/2. And I'm going to leave that unmultiplied. The new power will be -3/2. When I do the third derivative, the -3/2 is going to multiply to these two things. So I'm going to leave it unmultiplied. Let's just do one more. Okay, now when I plug 0 into all of these, the term in the parentheses will become just 1, and 1 to any power stays 1. So the thing that we're going to get in all of this is just the coefficients. Let's create this Maclaurin series, grab the general formula, and let's start plugging in some of these numbers and see if we can figure out patterns. All right, plug this in first. Then this goes in next, times the x. The next one's going to be this right here, times x squared, and that's over a 2 factorial. Right, you see what I'm doing here? And then we're going to have that is our coefficient over a 3 factorial times x cubed. And let's just stop there. This particular case, it can be quite tricky to turn this into a summation notation. We could try to simplify these coefficients and see if they simplify to something convenient. But this is actually quite a complicated one to come up with a general formula here. What we're going to do is we're going to create a general formula on the next slide, and then we're going to return to this one and see how it might look. So this next example is the same as this one, except that I'm putting in r as the power, whereas in this case here, that r happened to be 1/2. What we're going to do is create what's called the binomial series. It's a series of x plus 1 raised to some power. The original function is just x plus 1 and being raised to the r. First derivative, the r would drop down. The new power would be r minus 1. And the chain rule would not change anything. Second derivative, and then we have x plus 1 raised to the r minus 2. Third derivative, now we have r times r minus 1 times r minus 2 times x plus 1 raised to the r minus 3. You start to sense a pattern. Complete our table here and plug 0 into all of these. I'm going to get 1 as the first result. The next one's going to be r. The next one's going to be r times r minus 1. Then it's going to be r times r minus 1 times r minus 2. So when I go to my general formula, and I start replacing these components with what I have in the table. So f of 0 becomes the 1, f prime becomes just r, and that's times an x. The next one's going to be r times r minus 1, and then stop, and divide by 2 factorial, and then x squared. The next one's going to be an r times an r minus 1 times an r minus 2 over a 3 factorial, and then there's going to be an x cubed. Okay, let's actually do one more here. And the next one's going to have an r times an r minus 1 times an r minus 2 times an r minus 3. So it's going to be 4 numbers being multiplied there, starting with r and then counting down by 1 each time. And then that product will be divided by 4 factorial, 4 numbers divided by 4 factorial times x to the 4, etc. The pattern I just established is consistent. We just have a 1 to start. Now we have one number and a 1 factorial. Then we have two numbers and a 2 factorial, right? Three numbers and a 3 factorial and a 3. So the number of numbers being multiplied in the top and the factorial and the power all match from term to term. So we actually invent a notation for these things. The first one is 1. And then I'm going to put this r over a 1. It's not a fraction. Don't put a line here. The way you say this is r choose 1, and it's times an x. The next one, this expression here, we're going to represent with a new symbol called r choose 2. This next coefficient right here, we're going to say is r choose 3, and that's being times an x cubed. Then we have something called r choose 4 times an x to the 4th, etc. Now I'm finally able to say we can express this as r choose k times x to the k, starting at k is equal to 0 and going to infinity. This is called the combination. When you plug in 0, we get r choose 0. So the combination is 1 by definition. And you plug in a 0 for that k, we get an x to the 0, so we also get a 1. So this formula leads to this 1. And then we plug in k equals 1 in both spots. And so we get r choose 1 times x to the 1. Then we get r choose 2 times x squared. And then r choose 3 times x cubed. And then r choose 4 times x to the 4th, etc. And then how to interpret these combinations, for example, r choose 4, there's going to be two parts. You're going to turn this combination into a fraction. The first part is the numerator. It always starts with r, and then you just keep decreasing by 1 until you have 4 numbers, until you have this many numbers. And your denominator is simply a factorial of whatever that is. Just for example, if r choose 5 means this. Start with an r, and then keep removing 1 until you have this many numbers. So we actually stop at r minus 4. There's 5 numbers there being multiplied. And then you divide this by that number, which is 5 factorial. Okay, so you can use that meaning for even r choose 1, as low as r choose 1. Because if I say do r choose 1, then I start by doing r, but I stop after I have one number, which I do already, and then I divide by 1 factorial. So this combination here just gives you that r. You could do the ratio test on this to find the interval of convergence. And when you do, you're going to find that the interval of convergence for this series is just -1 to 1, exclusive of the endpoints. So this allows us to say that if ever you have a function that's 1 plus x raised to some power r, it can be written as this series, which can then be expressed this way. This equal sign right here is true if x is somewhere between -1 and 1. Here's our more general statement. This is called the binomial series. It's wonderful because it can be applied to any case where you have 1 plus x raised to some power, which is exactly what we had up here. So the way we're going to write this actually, I'm not going to bother simplifying any of these things, rewrite them in terms of combinations. Well, the first one is r choose 0, and r in this case is 1/2 specifically. Any r choose 0, we're going to say is 1 plus. Now the 1/2 we have here is 1/2 choose 1, and that's times x. Then 1/2 times one number less than it is only two numbers, and over a 2 factorial, that's the same thing as 1/2 choose 2, and that's times an x squared. And this next one is 1/2 choose 3 times x cubed. To do 1/2 choose 3, you would start with a half, do one number less, and then one number less than that until you have 3 numbers, so we stop there, and then we divide that by the 3 factorial, etc. So if I write this one in series notation, we just say 1/2 choose k times x raised to the k. The very last thing you might be expected to do here is just to write out some of the terms. We can actually now bother trying to simplify these terms. So this would be 1/2 x. Here we got some work to do. We're going to have -1/4 divided by 2 factorial. That's going to be -1/8 x squared. The next one, when you multiply these things together, you're going to get +3/8, and that's divided by a 6 times 1/6. I'm getting a 1/16 out of that times x cubed, and then etc. It's really hard, without doing the calculation, to predict what the next term is going to be. Looking for a pattern just from these. Okay, this is how you make Taylor series and Maclaurin series out of functions.